Nobody's here yet, but we're going to just start by opening up our new files for day 4. Alright, we have a blank file. We're going to put in the standard Haskell preamble. Normally in a library you would use hierarchical module names. We're writing an application, so just calling our modules day 1, day 2, day 3, day 4 should be just fine. We'll add an export list later and probably some extensions at the top of the file. Let's see. If we take a look over here, day 3's file, you'll see we have at the top, like I said, some extensions. We have an export list, some imports, and we have, of course, the code that we're going to write. All right. So first thing we're going to do is that I like to treat all of these problems as a parsing problem. So we're going to start by importing the libraries and symbols that we need in order to parse this giant map of rolls of paper. And in fact, we're going to do one thing first. Before we write the parser, we're going to define some types that represent the underlying data. Alright, we're going to import this, and you'll notice I have the Haskell Language Server running, and it has already complained about something, and I'm going to fire up the code actions that it suggests for that error. You'll see number 1 is add import qualified post. That's an extension that I like to use. There it is. We're going to save the file, and we're going to and we're going to run the formatter. I sometimes wish the Haskell Language Server would run the formatter, or would run its suggestions according to the formatter, but it doesn't. That's okay. Eventually I will trim down that list of what's imported from data.vector, but for now we're just going to import everything. We can always trim down the import list later. Alright, so alright, we're going to create a data type for the warehouse floor, and this is a common convention. In Haskell, the MK means make warehouse floor. We're going to have one constructor for this data type. And this is a style that you may not see elsewhere, but it's common in Haskell to have brace thing, and then on a new line, comma, next item. And so we're going to follow that here. All right, we have and we're going to add. So what I'm thinking is that in order to solve the problem, we're going to have a flat vector. We're going to have we're going to store with it the length and the width so that we can treat the flat vector as if it actually were a two-dimensional array. And then I'm going to, so we're going to have the content, the width, and the length. And we're going to, this isn't strictly necessary, this is a toy, but for small types like int and or int64 or word64, it is very often useful to embed them in the data structure with the unpack pragma. Alright, so here's the length. I prefer to use types with explicit sizes, for instance, int64 versus int. But int is going to be used to index the vectors, and so the path of least resistance is to just stick with ints in this case. So let's see, it's complaining about a couple things. First of all, we can solve that one by just importing, or by using the correctly qualified name for vector, and then we're going to hit the code actions again, and it's going to give me a bunch of options. It's usually faster for me because I know exactly which one of these I want, and so it's just pattern recognition. But in this case, the one that we want is number 3, import data.word8. I prefer explicit import lists. So, all right, now we have our warehouse floor. All right, so we're going to build up our parser, and we're going to do that. Hello, I see I have some viewers. All right, so we're going to start our parser. If you've seen the problem, we're only parsing 2 symbols, and so we're going to go ahead and start building out our parser. We're going to borrow the imports from over here just because I know that that's what I need. And in fact, we're only going to import parser. So let's see. All right, our vectors are word8, and we're going to go ahead and just do the smallest parser that we can. Let's see. And so it's going to parse a word8. All right, and we'll go ahead and write a definition for that. First, we have all right. We're going to use the string function from the parsing library, and in a second we're going to get a complaint, and we'll pull in the overloaded strings extension. And if you're not familiar with that, feel free to ask a question and I will explain it. All right, so we have 2 branches, and I'm actually just going to lean on the linter because I don't know exactly the precedence of the operators, and I'll just let the linter tell me what needs, if I have any extraneous parentheses. All right. So this star operator here may not be something you're familiar with. Essentially, it means take the effects of the thing on the left and ignore the result of the thing on the left, and return, and then apply the effects of the thing on the right and keep the result of the thing on the right. In this case, the string parser will return the 1-character string dot, which we don't care about, we're going to throw away, and then the effects of pure has no effects, and we're going to keep 0. So you can read this as this parser recognizes the string dot and returns 0, or the string at returns 1. We're going to use those to represent whether or not there is a roll of paper in this particular tile on the floor. And we actually need this particular case. Actually, we don't need that case. So this parser will fail if it doesn't encounter either the string dot or the string at, which is fine because we want it to fail. And we will actually lean on it failing in a little bit when we build up in larger pieces the parser that parses an entire row. All right, let's see. So we have the linter complaining at us. Let's see what the code action is here. All right. Let's see. Okay, yes, we're going to apply hint 3. Very helpfully, it's going to suggest that instead of using pure, I just use this other operator, which incorporates that call to pure. All right. And down there at the bottom, you can see 28. That's the one that we want. Import data.functor for that particular operator. And now we can see it's complaining about our use of string, which we haven't imported. Haskell Language Server to the rescue. We're going to import string. We're going to add it to the import list. And whenever I do that, I always reapply the formatter to make sure they're in the correct order. And now there's another complaint. Like I said, it's going to complain that this is not a piece of text, but rather a list of characters. And so we're going to enable another extension. Let's see what the error is. Yeah, okay. We'll just do it ourselves. All right, so that's that. All right, now this pipe angle operator is an alternative operator and hasn't been imported. It's not available by default, but there's an easy solution to that. We're just going to import it, and we happen to know that the one that we want is number 11 down here. We're going to import it, and rather than name it explicitly, we'll just import all of the things that go with alternative. All right, now we're going to apply the same lint. That's what the blue here means, is that this is a lint warning. We're going to apply the same hints. So we're going to use that operator, and now we're good. Okay. Now, all right, so now we need to parse a row of tiles, and we will eventually turn them into vectors, but it's actually easier as we're parsing them to produce a linked list. So and I'm sure what we want is many1, which is from attoparsec.text. That's the one we want. And you give it a parser, and as long as that parser so the parser must succeed at least once. This is important. It helps avoid degenerate parsers that loop forever and don't take any input. And then we're going to basically take as many parse tiles as we can, and then the thing that we expect is the end of line. And in fact, what we actually want is not this, because I am uncertain whether the file as generated by the website contains a trailing end of line. And rather than worry about that, I'm just going to use a little helper I wrote on day 1 that will be satisfied if it finds either the end of the line or the end of the input, which is perfect because that's what we want, is that we want to find the, we want to stop when either we run out of input or we hit a new line. All right. And now, and we can make sure that these are working. We're going to write a comment that we can evaluate. Let's see. So we're going to need one additional file, or one additional symbol that we aren't importing into the module. And then, actually, we can do, where did this go? All right, we can do this. All right, and then if you can see, it's kind of dark, but we have the evaluate text up there, and that's an executable code lens, and we just tell the language server that we would very much like to execute it. We get our result, which is good. That's what we want to see. And then if we change this, we get, again, what we'd like to see. And all right, and then we get an error message. We could try and do something with that error message or produce a better one if we were trying to have a user-facing parser, but this is not going to be a user-facing parser. We expect that the input that we download really ought to match this format. So we're just going to make sure, as long as it does fail, that's good. That will mean that when we get one row's worth, we actually stop at the end of the row. All right, and then we can do the same thing here. Oh, yes. Helps if I include the parser in the arguments. If you're unfamiliar with Haskell, arguments are applied just by juxtaposition. So there's no parentheses necessary in order to apply arguments to a function. All right, and there we go. We can parse a list, and that's what we expected. That's perfect. All right, now we're going to write, make sure this is where we want it. Now we're going to write a parser for essentially the entire file. And this one will be incredibly easy because we can use that same many-one parser combinator and produce the result we're looking for. Ta-da, that was surprisingly straightforward. And we can even just paste this, do this. And we just hit, hit refresh, and perfect. We correctly parsed all 3 rows of our tiny example. All right. Okay, so we have parsing kind of down. Now, let's see. we need some way of taking a list of word 8s and producing the data type that we have above to represent the warehouse floor. Now, this parser could be a little stricter. For instance, we could have a stateful parser that passed data through, and after the first row refused to accept any rows of a different length. But we're going to take this shortcut because this is advent of code, and just go ahead and assume that they are all the same size. We could actually add a check at the end when we produce the data structure, that at least we have the correct amount of data, and that would mean that we accepted input that wasn't correct as long as the first row had the correct number of rows. That would set the size. I think that's reasonable. All right, so here we go. Yes, I would absolutely recommend autoparsec, especially if it's not user-facing. Autoparsec is very good for quickly parsing data. There are two other libraries. There's Parsec, which I wouldn't use except as technical archaeology at this point, and also there is Megaparsec, which is almost as fast as autoparsec. It produces much better error messages, so if you're trying to do something user-facing, it's probably what I would reach for. Autoparsec has the nice property that you can feed it incremental input. It doesn't need access to all of the input at once. In this case, I already have written a utility to basically do all of that for me, but I'll walk you through it if you have more questions. Yes, and that's actually one of the reasons that I reach for Haskell often, is because so many things that I have to do involve some amount of parsing, and having a tool like autoparsec around just makes life really, really nice, because I don't have to like just split on something and hope that works. I can actually write a real parser with real tests. So yes. All right, let's see what else we got. Okay. Okay. Let's see. All right. No, I don't actually do Haskell for my work. That's one of the reasons I'm doing it for Advent of Code, is it's an opportunity to use this thing that I love that I don't get to use on a day-to-day basis. I do have a website that I am working on building in Haskell, mostly as an excuse to goof off with Haskell than to actually produce the content. Let's see. All right, so we're going to build a warehouse floor. We're going to take that list of word 8s, and we're going to produce a warehouse floor. All right, so this is a common convention. That double S there means the one S would mean a single list, and two S's. Let's see. And in fact, we're going to just throw out, or we're going to explicitly produce an error in some perverse cases that we should never run into in real life. So if you give me an empty list, then there's nothing going to get produced. All right, the error function actually is a very interesting function in Haskell, because it will you give it a message and it will produce a value of any type. This is a little different from what you might find in other languages. You can actually have a value whose value is error, and because Haskell is lazy, until you inspect that value, you don't actually have an error. All right, so we're also going to handle this case. Okay. All right, so this is a destructuring. It says, okay, that outer list, if the first item in it is the empty list, and then the remainder is whatever, we're going to produce a similar error. In production Haskell, you would probably, instead of just calling error, you would have explicit exception types and possibly catch them. Again, this is advent of code, so we're just going to take the shortcut and just call error. Let's see. Okay, attempting to produce and do it. Oh. All right. And the warning here is that the compiler is very helpfully telling us that we haven't handled all of the cases. Thank you very much. Okay. All right. So actually, we're going to introduce let here. All right. The width is just going to be the length of the first row. Oh. All right. And then and in fact, I'm going to introduce something else. Okay. Well, we'll do this. It says that I created a conflict between the actual function length, which is in scope, and the name of this field. But we're going to do this. There is an extension that says just don't generate that function. And we'll get later to how we access that particular field in the record. You can use destructuring. There's an update syntax, and there's an additional extension, overloaded record dot, which lets us use Java style, container dot field name. We'll see if we need it later. So the underscore here, while you're writing Haskell, you can put underscore anywhere where you need either a type or an expression. And the compiler will helpfully tell you, for instance, what the inferred type is for the expression you've written, or what the inferred type is where you put the underscore where it was expecting an expression. And it can be useful if you're trying to figure out what needs to go here. Let's see. So this says the inferred type is list of A to T, right? Like, because we haven't done anything concrete with either the elements in the list or what we're going to produce. So both of those, as far as the compiler is concerned, are unconstrained. So, but we know that this only needs to work on list of word 8 and only produce warehouse floors. It's not going to produce anything else. All right. Let's see. We want from list, and the list we want is is to take those lists of lists and produce a single list. That's what we want. All right. And then if we ask the compiler, hey, what's the error here? It will tell us we found a hole of type warehouse floor. So we need to build something of type warehouse floor. All right. And we're going to do this. And we're going to, it's going to complain about this for just a second, but there is there's an extension that will let us just pun these, meaning instead of writing width equals width, if you have something in scope called width and a field named width, it will happily. And as we ran into before, there's already something in scope named length, which gives us the length of a list. But that's not what we want in this case. We want numbers. Okay, now let's see what the errors are. Illegal use of punning field. Okay. We're going to go ahead and follow the recommendation and add named field puns. And now, what is it complaining about? All right, we're just going to do this. We're going to do the prelude is the set of symbols that are automatically imported into every Haskell module unless you explicitly import the prelude. And all right, and then we can do this. We can call p.lengths, and now there is no conflict. And in fact, we could just do this if we're going to go that far. All right. Okay. We're going to import another utility. This one from data.function. And the I don't know if any of you've seen Elixir with its kind of pipelines, but the closest thing to Haskell to that pipeline operator is the ampersand operator. In this case, the braces ampersand operator means that we're going to take this function and we're going to apply it inside of whatever effect is already there. In this case, this might fail to parse, and so we're going to apply the function that we have to the successful results, and we're going to propagate any parsing errors unmodified. Let's see, and before we try that, we're going to make sure we do this. So EQ means that we can compare these two things if they're equal. It's often useful, not a problem in this case. ORed means that we can sort these. But the important one here is show, which says the compiler will generate for us the ability to take the piece of data and turn it into a string for us, which is what we're going to do here. There we go. All right. So we correctly produce the flattened array 0, 0, 1, 0, 1, 0, 1, 0, 0. The width is 3, the length is 3. Perfect. That's exactly what we want. All right. And all right. And we're going to review the problem off screen. Let's see. Fewer than 4 rolls of paper in the 8 adjacent positions. Okay, which essentially means that if there's a roll of paper in the corner, it's always available, because we're treating the extras around the array as if they all were dots. We're looking at this array as if it were placed in an infinite grid of dots, and we're just looking at this subgrid. Okay, so okay. All right, so we're going to need something that can count the adjacent rolls given an X and Y position. There's a part of me that is thinking very hard about this as a before my current job, I worked at a computer vision company, and this looks very much like a convolution. If I had to solve this on an FPGA, that's what I'd be doing. But I think just doing the indexing nearby ought to be just fine. So, all right. All right. We need a, oh. And since they're stored as word 8s, we might as well just sum them up. All right. Okay. So we'll go ahead and width, that's right. Okay, so Y is going to tell us how many rows we skip, and okay. We're going to need overloaded record dot. We'll go ahead and format things. Okay, so that we sort the import or the extensions. Okay. Let's see. Okay. So first we'll get the indices that are just up by 1 and just down by 1. Then let's see, no. Data vector. All right. Pause with me. I'm going to briefly look up I'm looking up data vector unboxed. I don't always remember things. I'm trying to have more of it memorized for streaming. And the function I'm looking for is indexing. Yes. Oh. Okay. Yes. All right. And we're going to use the safe indexing. No. Okay. All right. So not quite, because that would cause wraparound, which isn't what we want. Okay. We're just going to write a function to check our indices, and we're going to check the 8 around. So we have yeah, up and down should be fine, because if we go up and we're off, and we go down and we're off. And then okay. We will send them as pairs. So index 0. The reason we're sending them as pairs is once we have, if we just add and subtract, we lose the ability to check against the right and left edges. Whereas if we keep the offset, we can write check index in such a way that if, for instance, if the index or if the offset is negative and we're at the left edge, then we just return a 0. And if the offset is positive and we're at the right edge, we can just return 0. So and we're going to intentionally leave this one off because we don't need to check that. Oh, it's complaining about that. That's okay. And then all 3 of those. Less than 0 equals 0. We're going to handle the exceptional cases first, and then we'll have a fall through where we do the standard case of just doing the lookup in the vector. It's greater than 0. And we can use if we handle the left and right, then we can fall back on the safe indexing of the vector to handle the top and bottom, which is, I think, going to be the cleanest way to handle this. And otherwise is just a synonym for true, but it's convenient. It's standard to write it as otherwise here. In fact, we're going to do this. There we go. It's often convenient to just let the formatter rewrite things for you. Okay. And in this case, we want to use the maybe function, and okay. We're going to use that operator, and it's imported qualified. All right, what is it complaining about? Okay, yes. All right, it says give me okay, so maybe is a useful function allowing me to convert a maybe value. Okay, maybe has type. Give me, okay, the failure case, the successful case, and the value. And it helps if you, all right, what is it complaining? Non-type variable argument. That's interesting. Okay, one thing that is useful when you get an error like that that doesn't quite track what you're expecting is to just start giving things types. It should take a pair of int, which is what the parenthesis comma means, it's tuple, and it should return a word 8. That's That's right. Okay, I want the identity function. All right. We're going to use from maybe. And then we're going to delete the qualifications here. And then we're going to let the language server do the import for us. All right, there we go. All right, so our bounds checking for left and right should do its job, and then the built-in bounds checking at the end of the array should work for the top and the bottom. Okay. We're going to copy this example. And the center of this, let's see. All right, and we're going to take advantage of the fact that if Haskell has automatic currying. So if I count adjacent roles and I give it 2 arguments, I'm left with a function that's expecting a warehouse floor and is going to return a word 8. So we're going to just give it these 2 arguments, and then we're going to evaluate this. And perfect, we get what we're expecting. So we can parse an array of these things, we can build the warehouse floor, we can count the adjacent roles at a specific square, and that will give us 2. All right. So I am planning on wrapping up in, let's pull back to the comments. Let's see. Sorry, I didn't have the window on the comments. Let's see. I haven't ever tried any of the alternative preludes. This is NeoVim, not with tmux, just NeoVim Qt. So whether or not you give things types to begin with is a matter of style more than anything else. So I find it very useful when I sit down to write a piece of code to write the type first, so that I get help from the compiler to tell me whether or not what I've written matched at least some summary, high-level summary of what I intended to write. So I actually, it's very common for me to write types for high-level things. I rely on type inference for example, like all of these lets here, right? Like it would be annoying to have to tell the compiler that basic index is an int when no, the imports in the comments, that's part of there's a plugin for the Haskell Language Server that will evaluate expressions. That's what the 3 arrows is. And in order to evaluate, sometimes there's a symbol that isn't imported into your code that you would like to be available in the as it evaluates this bit of comment code. So for instance, parse only here, and this angle bracket ampersand operator are not imported into my code. I'm not using them anywhere, but they're very useful in running the example. And in fact, there's a plugin or there's a tool you can use to essentially turn these into unit tests to make sure that the examples are still correct. But I find it very useful as I'm writing bits of code to just be able to drop these comments in here and then tell the language server to evaluate them as a very quick check that what I have is what I intend to have, without having to go to a separate window with a REPL. All right, so I'm probably going to wrap up in about 5 minutes, so we may not get through the whole problem, but that's okay. Essentially, we're going to loop over the entire 2D array linked with, and we're going to find number one, we're going to find roles that have exactly, or we have less than 4 adjacent roles, and we're going to count those. So now that we can count the adjacent roles, it's simply a counting problem where we query. Basically, we walk the entire array, we count the adjacent roles in the array, and we sum the roles that have fewer than 4 adjacent roles in them. Let's see. All right. Oh, the window manager is, I did see it. It's just LXQT. I've used a bunch of different things. I like things that get out of my way. I might try something else if I really need, if the world moves to Wayland before LXQT really gets there in a convenient way. But they're working on it. I tried it, it wasn't quite production ready yet. All right. All right, it's complaining that I don't have word 64 available, and now it's complaining that I don't have a definition for this. I could just do this, and then it's often useful sometimes to go to say to yourself, I'm going to need a function that with this type in order to solve this problem, and then just write it as an underscore, and then write the rest of the thing, and then go back and now solve the small problem that you've left for yourself. But we're going to go ahead. Okay. We're going to use a list comprehension here. X comes from the range 0 to oh. We're actually going to do this. Wrong way. Width. And Y comes from length. And we're going to introduce this, which we haven't used before, but is convenient in this case. Where is similar to let. It's often convenient to, just like I mentioned, sometimes it's convenient to write the type of a thing and put underscore and then come back to it later. Sometimes it's convenient to push a definition to the end of a function, especially when once you have those definitions, the function body is very short. So in this particular case, what we want, and all of the arguments will be in scope for the where as well. So actually, we can push this part here. Okay, so we're going to borrow this line because we need it again. I probably should make that a, if I find myself borrowing that again, I probably should just make that a function. But we'll just borrow it for now. Okay. Then we're going to, let's see. Okay. All right. So if it's not a role, then we're just gonna return 0 because we're counting. Let's see. All right. If all right. And we're going to borrow this comment again. Only instead of counting them at a single spot, we're going to count them everywhere. All right. Oh, haha. Perfect. So we have 3 movable roles. It's going to be short work to wire these up and make them accept the file and post the results to Advent of Code. When I'll go ahead and I'll leave this one up on my channel, and I will put the code repository in the description. So, all right, thank you very much.